although weak acids are basically just another type of equilibrium situation for us to deal with, polyprotic acids add kind of a twist to this. So polyprotic acids are ones in which you have more than one ionizable hydrogen. So you can see the table here that going on down several examples here, we've got ascorbic acid, which is vitamin C, 2 acidic hydrogens. Citric acid actually has 3 acidic hydrogens. And so you notice that many of these are organic acids, and again, they have rather small Ka values. So the Ka1 represents the ionization of, or the dissociation of the first hydrogen, and then the Ka2 would be the subsequent ionization of the second hydrogen, and then the Ka3 would be for the third. This will become kind of obvious how we deal with this when we look at the example at the bottom, which says, what is the pH of a 0.2 molar solution of vitamin C, which is ascorbic acid? And typically you want to also determine the concentration of the anion, in this case the ascorbate ion. All right, so given that this is an equilibrium situation, we're going to use our table. So we'll write down our equilibrium expression. Again, the ascorbate ion, or ascorbic acid, excuse me, is H2C6H6O6. And so that's going to be in equilibrium with the H plus the HC6H6O6 minus. And so according to the table, that Ka1 was equal to 8 times 10 to the minus 5th. In our table then, we've got our initial, our change, our equilibrium, and we've got our acid, so we'll just abbreviate that as H2A this time, H plus, and HA minus. And we'll go ahead and fill in our chart at 0.20000 plus x minus x, 0.200 minus x, x. And then we go ahead and do our typical equilibrium here, where we'll have the Ka1 equal to 8 times 10 to the minus 5th, which would be equal to the H plus times the HA minus. So it would be x squared divided by the concentration of the acid, 0.200 minus x. And of course, we're going to take advantage here of the small value of the Ka and the relatively large concentration of the acid. And we're going to assume here that 0.200 minus x is approximately equal to 0.200. So the x is negligible there. And then we'll continue our problem. So if we do that, we end up with a value of x of 0.004. And if we go back and check our work here, 0.004 compared to 0.200 is approximately 2%. So that's less than a 5% error that's created from making that assumption. So we can go ahead with that. Now, where do we go from there? So what we've done is we've figured out that from the first equilibrium, that the H plus concentration, which is equal to x, is going to be 0.004, and that virtually the concentration of the acid itself, that 0.200, will not change significantly, and will also form 0.004 molar in terms of the HA. Now that's the part that we need to consider in addition here. So let's go on down a little further, and let's write that equilibrium. So now we have that HA minus in equilibrium with H plus A2 minus. And this Ka value from the chart on the prior page is equal to 1.6 times 10 to the minus 12th. We're going to go ahead and draw our equilibrium table again. or our ice table. We've constructed another table. This time we'll label it with HA minus, H plus, and A2 minus. Initial, change, and equilibrium. Now, the thing I guess we have to remember is that both equilibriums here are happening simultaneously. So it kind of complicates matters. But what we'll have to do is make some assumptions to make our work actually manageable here. So if we look back at our equation from before, we can imagine that initial that equilibrium concentration of the H plus right here, and the equilibrium concentration of the HA minus still exists as we do this new equilibrium. So if we come down here, we can fill in those values into the table. They were the value of x, so the HA is going to be 0.004, no significant figure. HA is 0.0040. Common misconception here is people plug 0 into there, which it's not. And then 0 for the concentration of the ascorbate ion, the A2 minus. Obviously, we've got to go in the direction of the right, so this is going to go up by x. Excuse me. This will go down by x. This will go up by x. This will go up by x. So obviously, this is a new x, so let me put x prime in each of these. What we end up with then when we fill in our box is 0.004 minus x prime, 0.004 plus x prime, and x prime. Now it's time to look at that value of the equilibrium constant. So that equilibrium constant is 1.6 times 10 to the minus 12. Extremely small. This will always be the case. That second ionization, that second dissociation of the acid will always be much smaller than the first. And what this means is that the extent to which it's going to go in the forward direction, right, in this direction, will be very small. If you consider the fact that you already have a bunch of A minus in solution, right, we already have this whole big amount of H plus in solution, it doesn't take much to realize that minus x and plus x part are going to be extremely insignificant in these parts down here. So when we go down to do the equilibrium expression here, rather than having some kind of big jumbled up mess of a problem, we would say, all right, well, Ka2 is equal to 1.6 times 10 to the negative 12th, and that's going to be equal to the 0.004 plus x prime times x prime divided by 0.004 minus x prime. All right, and again, it's rather safe to assume that minus x and that plus x are going to be negligible. And so lo and behold, what we find out is that our x prime, which is actually equal to the concentration of our ascorbate ion, is simply going to be equal to our dissociation constant, our Ka2. Of course, I think we need to go back and figure out the pH. So we'd have to take the negative log of the H plus concentration, which would be the 0.004 up there. Now, so basically what we're saying then is that if you're looking at just the pH, the pH of a polyprotic acid is going to be pretty much exclusively based on that first dissociation that happens. So that first one up here where we figured out that X was equal to 0.004, which is the H plus concentration. Any subsequent ionization of hydrogens won't significantly change that value. So you can just do this first one to figure out the pH. Obviously, they force you into doing the second problem by asking you to determine also the ascorbate ion, the A2 minus. This cannot be done without doing the second equilibrium here. And of course, we'll see some different twists and things with this that'll force us to think a little bit.